What I want to do now is look at this thing called solids of revolution. And it's an application of integration. And what it involves is taking a curve like this one. Let me just cover up the bottom of this. Okay? So imagine we have a function, just a generic f of x here. And what we want to do is we want to find the volume of the solid that is generated when we take this curve and revolve it around the x-axis. In other words, I'm going to try to draw it for you, but here's the curve. Here's f of x, and here is kind of a reflection down here. Imagine a volume that's generated when we revolve this about the axis. Okay? You know, something like that. Imagine this volume that's generated when we revolve this curve about the x-axis. Well, that's what we want to investigate. How can we do this? And we're going to find that we can use integration to find that volume. And in particular, what we're going to use right now is called the disk method. So let's see how this works. Think back at when, and just focus on this curve, f of x. Think back when we first were introduced to integration and we looked at summing up some rectangles. We looked at these Riemann sums, right? So let's look at a Riemann sum here. Let me make a rectangle, and remember this rectangle has delta x, that's the width, and the height here, let's just suppose this is some x, the height here is f of x. Okay, so we have the area of this rectangle here to be delta x times f of x. Now, let's suppose that I take this rectangle and I spin it around the x-axis. Okay, so I spin it around the x-axis. Okay, like this. Okay, so I've got, let me shade it in here, maybe that will make it look a little better. So I spun it around there, and let me go ahead and complete the disk. Okay, so it forms a disk. Okay, my drawing is not that good, so you'll really have to use your imagination. So here's a disk. Now, think about what is the volume of this disk right here, this volume. Well, it's got a radius, right? The radius is going to be f of x, right? So we've got r equals f of x, definitely. And what is the height? The height is delta x, right? See, the height of this disk, it'd be the same as the width of the rectangle. And we know how to get the volume of a disk. The volume is pi r squared times h. Well, in this case, our volume would be pi times f of x squared times h, which is delta x. That would be the volume of this disk that we formed. Now, what if we do that? What if we want to get this solid from beginning with this point, A, over to this point, B? In other words, I want to find the volume of the solid revolution from A to B when I revolve this function, f of x, about the x-axis. Well, think about if we had a lot of these little disks. What we would do is we would add them up, right? And that would be an approximation for that volume. Just like when we were introduced to integration, we added up all the areas of those little rectangles, and that was an approximation for the area under the curve. Well, we want to do that for these disks. We want to add up all of these little things. Now remember, integration, what an integral does is it adds up an infinite number of things, an infinite number of these super small little, flat little disks, right? In other words, if we let delta x be infinitesimally small, let that go to 0, what we have is we have an integral. So we're going to integrate from a to b pi r squared times the height, right? pi r squared times the height. That's what it would be if we take the limit. In other words, if I add up all these things, what I've got is a Riemann sum. I've got f of x1, f of x2, f of x3, delta x1, delta x2, delta x3, and so forth. And the more of these little disks I get, the better my approximation for the area under or the volume. So what I'm going to do is I'm going to take the limit. I'm going to say, well, let this delta x go to 0. In other words, let there be infinitely many of these little disks. And when I do that, well, that is the definition of an integral. It's the limit of a Riemann sum. So this integral has this, that's the power of integrals. We can add up an infinite number of things. See, we're going to add up all these little disks and we get this. Okay, so let's see how this would work. Now, up here, realize I talked about taking this curve and revolving it about the x-axis. But, you know, what I was doing was, it was understood that I was revolving this whole region about the x-axis because we were coming up with a volume. In other words, if I were to describe this region here, I would say, well, it's the region bounded by x equals 0, x equals a, x equals b, right? Y equals 0, and y equals f of x. See? So it's bounded above by y equals f of x. It's bounded below by y equals 0. And then it's going to go from a to b. See? X equals a to x equals b. These are just lines, right? Vertical lines. So really, you could think of it as, well, I'm revolving this region about the x-axis. I talked about it in terms of the curve, and then that formed a solid. But let's see an example here. Let's suppose I've got a region defined by x equals, or bounded by x equals 0, x equals 1, y equals 0, and y equals x squared. So I've got this region. Let's see what that looks like. Let's see if we can piece it together to see what's going on here. So I've got, here's my curve, f of x, y equals x squared right there. Y equals 0, that's here. Here's y equals x squared, and we're going from 0 to 1. So I'm going to take this region right here and revolve it around the x-axis. So here we go. We've got our integral. We've got our bounds of integration. X is going from 0 to 1. We've got our pi. I'll put that on the outside because it's just a constant. And we've got our function. This is our curve. And remember, that is squared. That's the radius. And then we've got the dx. So there we have it. This is the formula that will give us the volume of that solid or revolution. So now it's just a matter of integrating. So we've got 0 to 1, x to the 4th, dx. And then we've got pi. Use the power rule for integration. And we've got 1/5 x to the 5th from 0 to 1. So let's see how that works. We've got pi over 5, and this is going to be 1 to the 5th minus 0 to the 5th. And of course, that's just going to be pi over 5. So that's how we find the volume of that solid, this region here, when it's revolved about the x-axis. Now, let's suppose that we change the region slightly. Let's suppose that we've still got x equals 0, x equals 1, and we've got y equals x squared like usual, but then we have y equals 1, not y equals 0. So let's see what that's going to look like. Let's see what that's going to look like. We've got, okay, here is my x squared. I'm going from 0 to 1. And here is the line y equals y equals 1 right there. So now look at this region. This region's a little different because now we have this region right here. Not this down here, but this one. So we have to pay attention. This is no longer y equals 0, it's y equals 1. So we don't have y equals 0 on the bottom, we have y equals x squared, and then up top we have this y equals 1. So this region, we want to rotate or revolve this region right here about the x-axis. Now let's think about how we would go about doing that. What we want to think about is this. We take this top function and we think, okay, if I just do pi from 0 to 1 of just this top function, which is 1, look what that will give us. If we perform this operation, what we're going to get is one big cylinder, right? We're just going to notice the radius is always 1. And what we're doing is we're revolving this whole region about the x-axis. And we're just going to get a big cylinder. Well, we don't want a big cylinder. We want a solid that we get from just this top part being rotated or revolved around the axis. So we've got extra stuff. We've got stuff that we don't need, namely this, everything below the curve. So what we want to do is we want to subtract off that solid. Okay? Which is x squared dx. See? So notice, it's as though I'm taking the top curve, that radius squared, minus the bottom squared. So here's the way I could look at it. I could look at it as the top, which is 1 squared minus x squared dx. Now, I don't want you to think of this as a formula, trying to learn a formula, the top squared minus the bottom squared. But try to reason through it. See, you're getting the big volume and subtracting off the little volume. So this is the integral that you would end up evaluating. And of course, I'll just do the first part of this. It's 0 to 1, 1 minus x to the 4th. Well, I guess I can go ahead and do it all. So this is going to be pi times x minus 1/5 x from 0 to 1. Okay, there it goes. And now let's see what we've got here. We've got pi times, let's see here, if I put in a 1, I've got 1 minus 1/5 minus putting in a 0. Well, that would just give me a 0. See? I put in a 1 and put in a 0. So it could get a little bit messier if this bottom bound were not 0, but fortunately it is. So this is going to be pi times 4/5. See? 5/5 minus 1/5. So this is going to be 4 pi over 5. Okay, now consider this region. Well, let's just do the same region. We've got x equals 0, x equals 1. We've got y equals x squared and y equals 1. But now, let's not revolve this region about the x-axis. Let's revolve it about y equals 1. So let's see what we've got going here. See if I can draw a little picture of our region. Okay, so here it is. And let's suppose this is y equals 1. So this is our region right here. Now this time, we're not going about the x-axis. We're going to take this region right here and revolve it about this line y equals x. Now, here's the thing with the disk method. Really, what you're trying to do always is find what the radius is. So let's think about we revolve part of this. Let's just look at this part right here. Let's suppose I revolve this part about the line y equals x and I get this disk. This is the radius. Now look, we're going to have pi from 0 to 1. That's no worries about that. But what is the radius? Well, it's this length right here. Each one of these, every time we rotate a disk around, we're looking at all the radii right here. Look, what these have in common is it's 1 minus x squared. That's the radius of each one of these. 1 is this whole thing. 1 minus x squared is this. There's 1 minus x squared, and you get that. So this is pi r squared, like that. So this is that solid. This is how we would rotate or revolve around the line y equals 1. So let's see what we got here. We've got 0 to 1, 1 minus 2x squared plus x to the fourth dx. And all I did was multiplied this out, and so I could use the power rule for integration. So here we go. Let's see what we've got now. We've got pi times power rule x minus 2/3 x cubed plus 1/5 x to the fifth. And we're going from 0 to 1. Okay. So let's see how that's going to look. Now I use these bounds 0 to 1 just to make it easy for the demonstration. These bounds could get more complicated. Maybe we go from 3 to 7, and then you see you've got a little bit, more opportunity to make mistakes. But here's what we've got. We've got pi times 1 minus 2/3 plus 1/5. Minus plugging in a 0. Well, when you plug in a 0, just everything is 0. So this is your answer right here. Now I'm going to do this. I'm going to factor out a 1/15, right? So I get pi over 15. And what I get now is I get 15 minus 10 plus 3. See? Now, all I did was I divided by what I factored out. Notice I said 1 divided by 1/15, I got 15. Now notice if I distribute back through, so this was just a little arithmetic trick. If I distribute back through, 1/15 times 10, that's going to be 2/3. 1/15 times 3, that's 1/5. So you see I get the same thing back. It was just a little trick to make things easier on myself. So now I get pi over 15, and now I get 15 minus 10, that's 5, plus 3, that's 8. So it looks like I get 8 pi over 15. Now of course you don't need to do the trick I did here, this little arithmetic trick. You could just, do the arithmetic in here and then multiply times pi. But you would still get the same thing, 8 pi over 15. So that's where, here's the thing. Each of these problems, when we're revolving around a horizontal line, it's going to present its own challenge. What we have to do is we have to figure out, well, what is the radius? Now notice, previously it was a matter of the top radius squared minus the bottom radius squared. This one was a difference of the radii squared, right? 1 minus x squared, the difference squared. So you have to look at each problem individually. Okay, so let's see how this would work. Now, up here, realize I talked about taking this curve and revolving it about the x-axis. But, you know, what I was doing was, it was understood that I was revolving this whole region about the x-axis because we were coming up with a volume. In other words, if I were to describe this region here, I would say, well, it's the region bounded by x equals 0, x equals a, x equals b, right? Y equals 0, and y equals f of x. See? So it's bounded above by y equals f of x. It's bounded below by y equals 0. And then it's going to go from A to B. See, x equals A to x equals B. These are just lines, right? Vertical lines. So really, you could think of it as, well, I'm revolving this region about the x-axis. I talked about it in terms of the curve, and then that formed a solid. But let's see an example here. Let's suppose I've got a region defined by bounded by x equals 0, x equals 1, y equals 0, and y equals x squared. So I've got this region. Let's see what that looks like. Let's see if we can piece it together to see what's going on here. So I've got, here's my curve, f of x, y equals x squared right there. Y equals 0, that's here. Here's y equals x squared, and we're going from 0 to 1. So I'm going to take this region right here and revolve it around the x-axis. So let's see how it would set that up. I've got an integral from 0 to 1. Okay. I've got the pi. Okay, I'll just put that on the outside because it's a constant. F of x squared. In other words, this curve, the function that describes this, or defines this, the algebraic function that describes this curve is f of x equals x squared. So this is going to be x squared squared dx.